For this video, I want to talk about how do we evaluate limits. And this is going to be a topic we return to frequently because this is going to be what's going to take some practice as you get comfortable with the idea of limits. And that's going to take a while. It's not going to be instantaneous. So let's first of all talk about the idea of a limit existing. So before we talk about evaluating, just does it exist or doesn't it? So a limit exists if you approach a real number. So a real number are the numbers you're used to. Whole numbers, negative numbers, fractions, decimals, both repeating and non-repeating, terminating and non-terminating, irrational, rationals. Those are all real numbers. Something that is not a real number is infinity. Infinity is the idea of an ever-growing number. And that's a very fine distinction, but it's something that we will practice. Infinity is not a number, even though it feels like we can treat it like one. Infinity is an idea. It's a concept, not a number. So if we say that a limit is approaching infinity, that's not a real number. And if your limit doesn't approach a real number, the limit does not exist. As Mean Girls so eloquently put it, the limit does not exist. So here in this first GIF, what we have is they're showing that, whoops, my apologies. As we approach 6, as x approaches 6, the function is getting closer and closer to a value of 4. So in this first GIF here, the limit as x approaches 6, and we're approaching from the left-hand side, so little negative signs say from the left-hand side, of the function f of x, is approaching a value of 4. So this limit does exist because as we approach 6 from the left for the x's, the function values, the y values, are approaching 4. A limit that does not exist, it can do so in different ways, and that's going to be something we have to practice. One of them being, let's say this is 6. If I approach it from the left, and we have a vertical asymptote there. At a vertical asymptote, the function doesn't exist, which isn't a problem for us with limits because we never reach 6. But as I'm approaching 6 from the left, my function is going off towards positive infinity, meaning it's getting ever larger. So I would say the limit as x approaches 6 from the left, this is for f, of f of x, I could say it does not exist, or I could say it's infinity because it's descriptive of saying, well, the reason that this limit doesn't exist is it's going off to an ever larger number, not a real number. Another way that a limit could not exist is a two-sided limit needs left and right hand limits to be the same. So if I say here is the x of 6, and let's say this is 5 and this is -2. Here, if I were looking at the limit as x approaches 6 from both sides, so no little sign there, and we'll call this g of x. Well, for the two-sided limit, the left and right-hand limits need to be exactly the same. Well, from the left, my function has values of 5. From the right, my function has values of -2. So because the left and right-hand limits are not the same, the two-sided limit does not exist. That would be the only reason then. If you're looking for kind of more visual approach, the GIF on this slide is showing, so here, what's happening at the point, the fact that there's an open value and the function doesn't exist doesn't change my limits. So it's showing different ways that the limit doesn't exist. So here, if there's an open dot, my function can still approach the same thing from both sides. That's okay. Now the left and right hand limits aren't the same, so that doesn't exist. The two-sided doesn't exist. Now my left and right hand limits are both infinite, and since infinity is not a real number, the two-sided the limits wouldn't exist. So kind of a graphical example of calculating these is here I have a graph. We'll call this for the function f. I have a and b. So on this, the limit as x approaches a from the left, well, as I move from the left, here I am at 0, 1, 2, 3, 4, 4.5, 4 3/4. It looks like I'm approaching 5 from the left. If I come from the right, I'm at 2.5, 3, 3.5, 4, 4.5, 4 3/4. Looks like I'm approaching 5 also. Well, because the left and right-hand limits are the same, the two-sided limit as x approaches a does exist and will be the same thing. If I approach b from the left and right, so the limit as x approaches b from the left, here I am at 3, 2.5, 2 1/4. I'm approaching 2. The fact that there's an open dot here doesn't affect because an open dot is only at b, and the limit says I never reach b, I just get really close to it. And so I'm getting really close to a value of 2 from the left. From the right, here I am at 0, -1, -2, -2.5, -3, -3.5, -3 1/4, -3 5/6. And again, I don't care that that's a closed dot, but it looks like I'm approaching a value of -4 from the right. Since the left and right hand limits are different, the two-sided limit does not exist. So graphically is going to be the initial way we look at evaluating limits because that's going to be the easiest one to see, quite literally. But it's not going to be our first choice most of the time when evaluating. This table here is kind of in order of use what we will use to evaluate limits. The first one being substitution. This takes care of like 95% of our limits. And what we do is we just plug the x value into the function and see what we get. We will examine why this works more in the next section when we talk about continuity, because it's tied to the idea of continuity. If that doesn't work, we see if we can simplify our function and then try substitution again. This is really nice when we have rational functions where we can factor and cancel things out. L'Hopital's rule is a special case that we will learn later. We have to learn some specialized calculus knowledge before I can even begin to explain L'Hopital's rule. So limits are going to be tough the first time through. L'Hopital's rule, we will revisit limits again, and you're going to find that by the time we do L'Hopital's rule, it's probably going to be around early November. Limits will have become much easier. The graph or table is the last method we use, really, and they're kind of the same way. We're looking at a picture of a graph or a table and seeing, okay, what does it look like they're approaching? The reason this is so far down here is it gives us an estimate. It's impossible to give us exact values. These are estimates because it's based on what it looks like. We're making a guess on a pattern. The sandwich theorem or squeeze theorem is a last resort. For years, they did not ask about this on the AP exam until 2019. May of 2019 was the first time in about 25 years that they asked a question on this theorem. And so I will go through it in a later video, but this is not one that we're going to spend a lot of time worrying about because the odds of this showing up on the exam are so tiny. And honestly, if you're at the point of where you are mathematically in high school, either you have to have a really strong knowledge of parent functions and their graphs and transformations, or you're going to need to look at a graph, in which case you'll use a graph or a table.